In this video, I'll briefly introduce the design of a high-performance dual-polarized tilted beam parasitic array antenna. There are two main methods to achieve dual-polarized tilted beam radiation. The first is using dual-polarized elements with a complex feed network, but these antennas are typically large, complex, and costly. The second method uses parasitic coupling in a Yagi structure, which usually works for linear polarization but struggles to achieve good dual-polarized tilted beam radiation. The main challenges are maintaining high polarization purity and ensuring strong isolation between ports. To address these, we've designed a high-performance, single-layered, dual-polarized, tilted beam parasitic array antenna. This design effectively resolves issues like complexity, low polarization purity, and poor port isolation. Our design uses a circular dual-mode resonator as the modulation unit for dual polarization. The polarization directions of the two orthogonal modes in the ARR depend on feed point positions. When these feed points are symmetrically placed at plus or minus 45 degrees, a pair of 45 degrees plus or minus linear polarization degenerate modes can be excited. By treating J plus or minus 45 degrees as a vector sum of J1 and J2 and ensuring their coupling strengths are equal, the array's polarization direction remains at plus or minus 45 degrees. The edge spacing G is key to achieving this balance. Once the modulation unit and G are set, we calculate the tilt angle and structure parameters based on refractive index modulation. According to the ARR's field distribution, the zero field regions of the two modes are separated by a quarter wavelength. This means two feed points, a quarter wavelength apart, naturally provide good isolation by being in each other's zero field region. Our final design consists of 5 dual-mode resonators with refractive index modulation and a pair of bent microstrip lines for feeding. The bending angle improves port isolation and cross-polarization purity while significantly affecting phase. With quantitative coupling control, the surface currents on each resonator align along plus or minus 45 degrees, achieving high cross-polarization purity. Simulation and testing results show fractional bandwidth for the two ports at 12.3% and 11.6%, with gains above 10.5 dBi and overall efficiency over 92%. Radiation patterns across different frequencies confirm a high XPD level with a stable tilted beam fixed at 45 degrees. In summary, compared to existing solutions, our design solves the challenges of dual-polarized parasitic arrays without needing extra feed networks. It offers wide impedance bandwidth, high port isolation, and maintains high cross-polarization purity even with large beam tilt angles. With its compact, single-layer design, this antenna is ideal for applications like base stations and similar scenarios. Thanks for listening.